I'm the developer of TorchRL, so it's the reinforcement learning library for PyTorch. But basically, my main responsibility within the PyTorch team is to help people that do reinforcement learning to basically solve their problems and bring that to the other members of the PyTorch team and see what we can do, to handle these kind of things. So let's keep going. So the things I'm going to talk about today are very, very fresh. This doesn't seem to work. Can someone go to the next slide?
You're getting more batteries.
Okay. Okay, awesome, yeah. So what I'm going to talk about today is reinforcement learning from human feedback. This feature in the library, first of all, is a prototype. So if you want to use it, it's amazing. What we really hope with this talk is that you're going to contribute. So basically to tell us what you think, to try it out for your problem, and basically come up with like queries. Oh, maybe you could do this and that, and perhaps even contribute, like write proper code and make it better. But okay, so why is it so fresh and hot? Well, basically I pushed the binaries 1 hour before coming here. So it's really, really fresh. And what is reinforcement learning from human feedback and why does it matter? Okay, so you all know about ChatGPT and all these kind of Gen AI models that we have out there and that are very popular nowadays. So basically what you usually do, what people were doing back in the days is that they were training those models on static data, things like Reddit or just text like books and these kind of things. And what they were doing is basically training the model to complete sentences, so you give it a sentence, you take off words, you have an incomplete sentence, just the first part, and then you try to generate stuff that makes sense. Yeah? Okay, let me speak louder.
We're getting batteries.
Okay, so you're trying to train this model to complete the sentences, okay? But the problem is that once you start talking with that model, that doesn't work that well. The problem is that you need a model, if you want the model to be really purposeful and useful, you need this model to be helpful, honest, and harmless. So basically, for instance, you don't want a model that makes things up. So we all know that we're still not there. ChatGPT and these kind of things still make things up, but they do a much worse job if you don't fine-tune them with the technique that I'm going to explain. Okay, so what you're going to do is that you have this model that you have trained on static data, and then what people do is that they train it using reinforcement learning. So reinforcement learning, very roughly, the idea is that you have an agent, so something that makes decisions, and you have an environment. The environment is basically the environment in which the agent is evolving, okay? So the environment gives to the agent a certain state, a certain observation, and based on that, the agent takes an action. And this action will trigger another observation, but also a reward, okay? And what you're going to do with reinforcement learning from human feedback is that you have your GPT model, and you fine-tune it using reinforcement learning. And so basically what you do is that you have a prompt, okay, just a text, for instance, from a user, like explain to me something like I'm 6 years old, and the generative model will output a text. This text is basically the action, okay? So it's basically what you do following the prompt that you just got. So we have the environment, it gives a state, which is the initial prompt, the agent, the model takes an action, and then it gets a reward. And the reward is something that people have ranked, So you have people like Amazon Turk and these kind of things that read the text that is output by the model, and they basically rank that. They say, oh, this answer is much better than this answer, which is much better than this answer. And then you have all those rewards, that are positive or negative or whatever, and then you fine-tune your model, basically telling your model, okay, try to do more like this and less like that. And it has a very strong parallel with the way you would basically raise a child. When you have a child, you tell your child, oh, this was very good. Oh, this wasn't that good. Maybe you could improve by doing that, and you give positive and negative rewards. Things like, oh, you did very well at school. Let's get an ice cream, and that's a positive reinforcement. So basically, we try to do the same thing with the model, giving positive and negative reinforcement to basically guide it through the correct behavior. Okay, so there are already many solutions out there to do RLHF, so the thing I just talked about. Most of them are very high level in the sense that you basically have a single entry point to a trainer class. So you create your trainer class that is basically the fine-tuning class for your GPT model, okay? And you just trigger that, you give it a data set with those positive and negative rewards associated with prompts, and then, okay. Can you hear me? Okay, that seems to work now. Okay, right, so you have your GPT model, okay? You have something else that I'm going to talk about, which is a reward model. So what you do is that you take this reward model together with your model, and you make your model work following some prompts, okay? So you give a prompt, you make the model work, it generates a sentence, and then you have another model, the reward model. I'm going to explain what it is a little bit later. This reward model kind of evaluates the answer. It says, okay, that's a good answer, that's a bad answer. And then you use this signal to fine-tune your model using the reinforcement learning algorithm, so the stuff that I'm making. So the solutions that you can find out there that do that, you know, the open source repositories that do that, the way they work is that you have this high-level trainer, you give it a model, you give it a reward model maybe, and then you give it a data set with prompts, and it's just going to do the work for you. You know everything under the hood, well handled, and like you don't need to worry about anything. The problem is that it works very well if your problem fits in, but if your problem doesn't fit in, and that happens very, very often because your data is formatted in a different way or these kind of things, then it's much harder to use, you know, because it's not that flexible. And also there is not an ecosystem for R&D, you know, in this kind of, with this kind of RLHF solutions. And finally, there is not a single way of doing it. So basically my point here is, imagine that you're a researcher or you're someone that knows very well the algorithm that is being used, and you use these kind of solutions. If you want to tweak the algorithm, you really need to go deep in the code base to change the various things that you want to change. And that's not ideal. So what we want is to have something that is a bit in between, you know, that is still easy to use, because that has a great value, that is still properly tested, but also something that is easy to hack and easy basically to recycle across use cases such that other people, basically my goal is not to replace those open source repositories. My goal is to give these guys the tools to make something that is still very high level if people need high level, but if someone wants to go low level and change the low level components, they still can do that. Okay. So that's basically what we want to do. Next slide, please. Next slide. Cool, okay, so let's get a little bit technical about it. So what we need is a generative model, so the thing like GPT, you know. You need some extra data, the data from Amazon Turk, you know, the people that looked at the answers and said, oh, that's a good, that's a bad answer, these kind of things. You need a reward model. So the reward model, basically what it is that it's a model that is very similar to your GPT model, but you replace sort of the last layers of the model just to output a scalar value. And then you you train this model to predict, based on the data, the extra data that you have, if a prompt is of good or bad quality. And so this model is just trained to say, okay, that's a good prompt, I give it a score of 1. That's a bad prompt, I give it a score of -1. And that's your reward model. And then the final thing that you're going to do is that after you have trained your model, you have trained your reward model like I just explained, now you're going to train your GPT model a second time using your reward model and an algorithm that we call PPO. So PPO is like the standard thing that people use in RLHF for some reason. I think it's because it's very data efficient, much more than many other techniques. But still, there's a huge gap in the literature because everyone is trying out PPO. And I think that one of the main reasons is that it's hard to come up with something else. And with TorchRL, it's very easy. If you have PPO and you have your RLHF algorithm, but then you say, oh, well, let's try something else. Let's try SAC, DDPG, whatever other algorithm we have. You can just swap things using TorchRL, and it's going to be very easy for you. Cool. Next slide, please. Oh, sorry. Okay, so this is from the OpenAI paper that explains what RLHF is. So here you have the collection of the demonstration data to train the model. Then you have the second thing, which is basically training the model based on the ranking, you know, so you have actual people that look at answers from the model and they basically say, this is better than this, which is better than this, etc. And finally, you fine-tune your model using the reward model that you have trained on this data and an algorithm called PPO. Next slide, please. So this is a fun thing. I went on ChatGPT and I asked, okay, was PPO ever published in a peer-reviewed journal or conference? And ChatGPT told me, yes, proximal policy optimization, PPO, has been published in peer-reviewed conferences, blah, blah, blah. It's ICML 2017, and actually it's completely false. PPO has never been published anywhere. It's kind of funny if you think about it, because then you can press this little button, you know, to basically tell the algorithm this is a negative reward. Next time you train the reward model, please consider that as a bad answer. But yeah, you can check it out. On 2017, there was no PPO paper. Anyway, just to give you an idea of how that works, right? If you say positive or negative reward, what they do with that is that they retrain the reward model. Okay, next slide, please. Okay, so TorchRL, what is TorchRL? I think it's a good time to talk about basically what the library is. So I mentioned some of it, but let me try to put it together. What time is it? Okay. So basically, TorchRL provides low-level abstraction for reinforcement learning, the thing that I said before, right? We want to give people that do reinforcement learning the very basic tools that they can easily put together to make a reinforcement learning algorithm. We have also high-level components that we mainly use as demonstration of how things should be used, such that it's easy for you to adopt TorchRL for your problem. Another thing that we want to do is to have a common umbrella for everything that is covered by the name reinforcement learning. And there are loads of things like finance, robotics, autonomous driving, many things use reinforcement learning. And fine-tuning generative models is one of them. And we focus on modularity. So basically what we want is to have a library where the components are really independent from each other, and also where you can use one component without using the whole thing. Because we don't think that adopting an entire framework is always the best solution. As a user, sometimes you're just like, oh, well, this component seems really amazing. How can I do to adopt just that thing? And that's really what we want the user to have as an experience. So it's not easy in reinforcement learning, because if you think about something like computer vision, in computer vision, it's quite easy. You know, you have images, you take the images from a data set, you pass those images through some transforms, then through a model, then through a loss, you backpropagate, train your model, etc. Everything is quite linear, you know. In reinforcement learning, it's not the case. Reinforcement learning is all the components are interconnected. Your transforms are connected to your model and to your repeat buffer. The data collection is tightly tangled with the kind of algorithm you're doing. So everything is entangled. Next slide, please. And like you see here, you have a policy, an actor that makes decisions. You have the environment we talked about at the beginning. And these guys need to talk. You need to store the data somewhere in a repeat buffer. Then you have your loss function that optimizes your model. And so it's very hard to put everything together. And so what we did in TorchRL is that we said, OK, wait a minute. What we need is the basic problem that we need to solve is how can we make something modular in which you can basically say, I just want to use the replay buffer and nothing else, but also make something that is well integrated, where things can talk to each other. And that's not an easy task, because it's really two things that are very further apart. And so the solution we came up with is called TensorDict. So TensorDict is basically a dictionary of tensors with some extra features from the PyTorch tensors. And it's super useful, not only in reinforcement learning, but also in many other domains. Next slide, please. So I'm going to talk just right now, next slide, please, about the data in RLHF, but also in TorchRL, because obviously those two things are very connected. Can you move to the next slide? Thank you. OK, TensorDict. So it's a dictionary-like and a tensor-like class. OK. So imagine that this is your data. It's a dictionary. It contains keys, and those keys point to tensors. And you have all those methods that you have in actual tensors, you know, data.cuda, data.float. You can put your data on disk using memory mapped arrays, or in this case, memory mapped tensors. You can do shape operations like stacking them and squeezing them. So basically everything is super intuitive and it's very, yeah?
What are you doing in those 9 steps?
Oh, it's just showing, displaying the kind of stuff that you can do. It's just a list. Yeah.
Okay.
But yeah, so basically you have all those features that are features from tensors, okay? So it's very useful for data representation, because imagine that you're doing computer vision, for instance, and you have a data set made of images and labels. Well, you can group those things together, and it's very easy to move them from one device to the other, to stack them together if you want to create a mini batch. It's very easy to index them, because you can take the first image and the first label just by indexing the tensor-dict. So basically, your life is made much easier when you're doing data representation. Next slide, please. Yeah, so this is, for instance, what it looks like tensor-dict in the case of RLHF. So what we have is, for instance, here pairwise data set. So it's basically a data set where we have chosen data, so data that has a positive reward and data that has a negative reward. And we need to have pairs of them basically for the algorithm. And here is very easy because we put them together and we know that every time we have, if we index the first item of this object, we're going to get one example of the chosen data and one example of the rejected data. Okay, next slide, please. Cool, okay. Two other things that you can do with tensor-dict, just going really quickly over them. You can do parameter serialization because it has a very nice nested structure. So you can represent the parameters of the model exactly in a structure that represents that mirrors exactly the model itself. And that's much, much easier than using stake-dict and this kind of stuff in PyTorch, you know. So we're actually right now working on potentially porting tensor-dict to PyTorch core to do parameter serialization in many different cases than just reinforcement learning. Okay, next slide, please. And finally, we have a whole set of primitives inside tensor-dict to do model execution. And so you can programmatically build a model just by saying, okay, here's a first module. It takes keys X and Y. And it adds them, a second module that takes X and A, it adds them, etc. And so you can programmatically build your model, then put your submodules together, and that's very easy to do, you know, and it allows you to control the flow of the model very, very nicely. Okay, next slide, please. Cool. So second thing that you need to do, so now we have the data represented as tensor-dict. The second thing that we need to do is train the reward model. So we provide some examples of how to do that in TorchRL. I'm not going to talk too much about that because that's like probably the least RL thing in the whole talk. Next slide, please. And finally, the fine-tuning. So that's the part that is really reinforcement learning oriented. So we have loads of primitives like loss functions. If you remember in the slide where I had the nice graph about the nice chart about how TorchRL works, there's a whole set of classes that is called losses, and one of the losses is PPO. So you can apply PPO to your problem without any problem. But as I've said, you know, you can really swap PPO with anything you want. And so I think it's a great opportunity for researchers and also practitioners to basically try out other things than PPO and maybe discover that there's another loss that works better and all these kind of things. And there are also loads of tricks in RLHF compared to regular PPO. Like, for instance, people have what they call the KL reward, and the KL reward is something that brings your model, keeps your model not too far from its original configuration, because the kind of thing that you see with RLHF if you just apply PPO out of the box is that it's going to go further and further, just optimizing your reward function, but not optimizing, but becoming more and more distant from the original model for some reason. And so the quality of the output degrades quickly. And so basically people could put those constraints here and there to basically force the model to stay close to its original configuration. And of course, we provide that in TorchRL. Okay, next slide, please. So this is a lot of code. I hope we can share the presentation afterwards, because like that you can have a look at it. But basically, this is how the KL penalty works. And basically, the only thing that you really need to look at is this, So you have your actor, so it's basically your GPT model. You put that in this thing, and you basically tell it, okay, right now, every time some data goes through this transform, you're going to add a little extra term to the reward to basically say, okay, try to stay close to the original configuration. Okay, next slide, please. Cool, okay, and so this is what the training script looks like. There are two slides like this. Here, what you have is just a function make loss, and you see that when we make the loss, it's super easy. It's 4 lines of code just to create PPO. And the rest is also quite easy. You make a reward model, you make a replay buffer to store the data, and all these kind of things. Like, you can have a look at on the repo, but what we try to do is really to have all those things, that are small components, and you can create them quite easily, and then put them together in Symfony and have something that works, out of the box for your RLHF training loop. Okay, next slide, please. And yeah, so that's what the training loop looks like. First thing we do is that we take some data, pass the data through the model, we ask the model to generate stuff, and then with the stuff that has been generated from the model, we pass them through the PPO algorithm. The PPO algorithm is going to produce some weight update based on the results, saying, okay, this was good, this was bad, this had a positive reward, this had a negative reward, so it's going to tweak your model to fit better the rewards that were observed, and then you go back to the data collection phase. Next slide, please. And yeah, so that's basically it for my presentation. Yeah, so as I said, RLHF is an active area of research. There are many things that need to be done, and what we hope is that by proposing this new product, we can help the people that are developing those techniques to do better, to more quickly try new things and maybe solve the problems. Yeah, so thank you.